Good day, I'm Norman Wildberger. In today's video we're going to carry on talking about the connection between the classical Brahmagupta's formula for the area of a cyclic quadrilateral and this quadruple quad formula that we talked about relating 4 points on a line. So it's actually quite interesting that these two somewhat quite different situations actually are intimately connected. And it's evidence for the power of thinking about things rationally. Okay, so what was Brahmagupta's formula? Well, it was concerned with a cyclic quadrilateral. That's a quadrilateral whose 4 vertices lie on a circle. And the classical formula is given in terms of the 4 lengths of the sides, A, B, C, and D. And here's one way of rewriting the classical formula, just involving a little bit of squaring. So 16 times the square of the area is this combination, minus A plus B plus C plus D times A minus B plus C plus D times A plus B minus C plus D times A plus B plus C minus D. And it's easy to remember because we're taking A plus B plus C plus D and looking at all 4 ways of introducing a single minus sign. In front of A, in front of B, in front of C, in front of D, and then multiplying those 4 terms together. Alright, so let's note a very important thing, that this actually works only for a convex cyclic quadrilateral. In other words, a quadrilateral that has roughly this kind of shape. Convex is a geometrical idea that's connected with the idea of ordering or betweenness in the plane. Okay, and we haven't actually defined convex, so let me just say informally what it means. Informally, it means that if you take any 2 points which are inside the quadrilateral, so that's assuming you have a notion of inside, then the line segment joining those 2 points also lies inside the quadrilateral. This would be an example of a quadrilateral which is also cyclic. It has 4 vertices lying on a circle, but it's not convex. So Brahmagupta's formula, even though I think he perhaps didn't say it explicitly, works for this kind of cyclic quadrilateral. The 4 edge lengths A, B, C, and D don't determine the cyclic quadrilateral uniquely. So there's 2 different kinds of cyclic quadrilaterals, one convex and one non-convex, that have in fact the same edge lengths in general. So here, this example here would be an example with this A being roughly the same as that A, this B same as B, this C the same as C, this D roughly the same as D. But this one's inscribed in a different size circle. So Brahmagupta's formula works for this one here. So in a quite different direction, looking at the geometry of a one-dimensional line, we introduce this function of 4 quantities called the quadruple quad function. And it was a rather involved algebraic expression. Here's what it was. So Q of A, B, C, D is by definition, first of all of this thing squared. And inside here we have A plus B plus C plus D squared minus 2 times A squared plus B squared plus C squared plus D squared. So all of that squared minus 64 ABCD. And this was very similar to the triple quad formula, or what we call Archimedes function. And we saw also that this inside here can be re-expressed in an asymmetrical form, and so we could replace it with 4 times AB plus CD minus A plus B minus C minus D squared. It's another way of writing this. And why was this function important? Well, because of this quadruple quad formula. That if A1, A2, A3, A4 are affine 1 points, 4 points on a line, and Qij is the quadrants between AI and AJ. And I remind you that that means the square of the difference between the coordinates of AI and AJ. Not the distance between them, not the displacement between them, but the square of the distance, the square of the displacement. So if we have these quadrants Qij defined this way for all I and j between 1 and 4, then the relationship is that Q of Q12, Q23, Q34, and Q14 is 0. That's the relationship between these four quadrances that we get by going through these 4 points cyclically. So in this example here, for example, we would have A1 at the point 0, A2 is at the 1, A3 is 3, and A4 is 4. Then the quadrants between A1 and A2 is 1 minus 0 squared, so that'd be 1. The quadrants between A3 and A2 would be 3 minus 1 squared, so that's 4. The quadrants between A3 and A4 would be 1 squared, which is 1. And the quadrants between A1 and A4 is 4 squared, or 16. And so the quadruple quad formula asserts that if we take these 4 quadrances, 1, 4, 1, 6, and we plug them into the quadruple quad function, we should get 0. Let's just check that that's actually the case. Let's use the second asymmetrical form. So if we take A times B, so that would be 4 plus C times D, say 1 times 16. So we have 4 plus 16, that's a total of 20 inside there. 4 times 20, that'd be 80. And here we have A plus B minus C minus D, so that's 5 minus 17. That'd be like 12. So 12 squared. 12 squared is 144. So 80 minus 144, that is 64. So 64 squared minus 64 times the product. Well, the product of all 4 is 64. So we have 64 squared minus 64 times 64, that is indeed 0. That's the quadruple quad formula, which is a direct generalization of the triple quad formula, valid for 3 points. But it's more complicated. We have more variables. The formula is a little bit more complicated, and we are also going up in degree. This is now a degree 4 expression, as opposed to a degree 2 expression for the triple quad formula. So what we're interested in is putting these two things together and asking, is there a relation between Brahmagupta's formula and the quadruple quad formula? And why might this be the case? So the justification is contained in our earlier work on 3 points and the relation with Heron's formula, or a rational version of it, which we called Archimedes' theorem. So let me remind you about that. So here's a triangle with side lengths A, B, and C. We're assuming here, just for the time being, that there is a proper notion of lengths. In fact, we know that's in fact very problematic, because lengths in the plane involve square roots. But this is the classical formulation of the theorem. So Heron's original formula can be rewritten by squaring both sides, essentially, to the following form. That 16 times the square of the area of this triangle is given by product of 4 things: A plus B plus C, minus A plus B plus C, A minus B plus C, and A plus B minus C. A similar kind of expression that we were just looking at for the Brahmagupta, except here we start with A plus B plus C, and then we multiply by the 3 different ways of modifying this one by adding a minus sign either in front of A, in front of B, or in front of C. And let me also remind you about the triple quad formula, which was a very fundamental fact about the quadrants is formed by 3 collinear points. So if A1, A2, A3 are 1 points, and Q1 is the quadrants between A2 and A3, Q2 is the quadrants between A1, A3, and Q3 is the quadrants between A1 and A2, then this particular quantity, which we called A of Q1, Q2, and Q3, which is Q1 plus Q2 plus Q3 squared minus 2 times Q1 squared plus Q2 squared plus Q3 squared, that's going to be 0. It's another way of restating the triple quad formula. And then we also saw that if we took this function of Q1, Q2, and Q3 and replaced Q1, Q2, and Q3, say by A squared, B squared, and C squared, then this expression factored. In fact, it factored into exactly these 4 products that was occurring up here in the Heron's formula. And this then allowed us to conclude that there was a rational form of Heron's formula. A formula that doesn't involve the lengths, but rather the quadrances of the sides. And the formula was that 16 times the square of the area is just the A function, this one right here, applied to the 3 quadrants of the triangle. Right? So we call this Archimedes' theorem, and this is a modern replacement for the classical Heron's formula, which is algebraically much nicer, which doesn't have any irrationalities in it because these are algebraic quantities rather than the irrational quantities that we generally have with lengths of sides of a triangle. All right, so this is our motivation, the fact that the classical Heron's formula is intimately connected with the triple quad formula. So it makes sense that the Brahmagupta's formula, which is some kind of extension of Heron's formula to cyclic quadrilaterals, might be connected somehow with the quadruple quad formula. All right, so we're motivated to look for a relation. And we probably should start with something like this crucial identity that connects the 2 aspects of things here in the case of 3 points. Okay, so there is such an identity, but it's a little bit more complicated than the corresponding Archimedes formula. Here it is. We're going to call it Brahmagupta's identity. Okay, and the identity is purely an algebraic identity involving this quadruple quad function Q that we had on the previous slide. The identity is that if we take this quadruple quad function and we substitute a squared, b squared, and c squared, and d squared for the arguments, then that expression that we have actually factors as a product of 8 different terms. They all look somewhat the same. They all have a, b, c, and d, but with different combinations of plus and minus signs. So let's have a look. The first 4 are familiar, in fact, from Brahmagupta's formula. There's minus a plus b plus c plus d, a minus b plus c plus d, a plus b minus c plus d, and a plus b plus c minus d. Those are exactly the 4 terms that appeared in Brahmagupta's formula. So that's good. What about these other 4 terms? What are they? Let's have a look. So we have to multiply these 4 by a plus b plus c plus d times a plus b minus c minus d, a minus b plus c minus d, and minus a plus b plus c minus d. Okay, we're doing some somewhat serious algebra here. Okay, so we have to go slowly. If you don't like algebra too much or are not too comfortable with it, this is a great place to slow down and practice and make sure you understand what's really going on here, because it's very instructive. So what we have here is something like we had for the Heron's formula. We have, first of all, the sum of all 4 terms. And then these terms are taken from this one by adding a pair of minus signs. Now if you have 4 places, then there are, in fact, 4 choose 2, or 6 possible pairs of 4 things that you can choose. So what we're doing here is we're choosing the 3rd and 4th, the 2nd and the 4th, and the 1st and the 4th to put the minus signs in. Corresponding to essentially the 3 different ways of subdividing 4 objects into 2 groups of 2. Okay, so this is an identity, and we would like to know, why is it true? We want to prove it. Okay, so let's take the quadruple quad formula first and insert a squared, b squared, c squared, and d squared. And here I've written the asymmetric form of it. So here we have 4a squared, b squared, plus c squared, d squared. And then in here there's something squared, and that is a squared plus b squared minus c squared minus d squared. So all of that is squared. And then this whole expression here is itself squared. And then we have minus 64 times the product of all of these things, which we can write as a, b, c, d, all squared. This is sort of analogous to the same kind of reasoning that we did with Archimedes' function, but it's more complicated because things are a little bit bigger. Okay. But what we did in that case is we recognized that we had a difference of squares, and so we're going to do the same thing here. There's a difference of squares since this is something squared, and this thing here is also a square because 64 happens to be 8 squared. So we can write this as a product of two things. So basically what's inside here, plus 8 times ABCD right here. And what's inside here, minus 8 times ABCD. Okay, so let's have a look at the first one of these things here. So we have a 4a squared b squared plus c squared d squared. Okay, and now if we square this term here, let's write that as a squared plus b squared all squared plus c squared plus d squared all squared. There's a minus sign here, so that will be a minus that and a minus that. And then minus twice the product of these two things. We're grouping this and this together. So twice the product would be 2 times a squared plus b squared, c squared plus d squared. There's a minus sign from there, and there's a minus sign from this times minus this. So we've rewritten this thing here, expanded it out using the binomial coefficient. We still have an 8abcd over here. And we can basically just rewrite the second term because it's exactly the same, except with a minus 8abcd. And so now we want to understand, why is it that this first term can be expanded to basically this first line here, and then this second term expanded to give the second line here. All right, so lots of fun practicing our algebra here. So I'm going to have a look at that first line that we had on the previous slide. Let's call that expression r. So here it was expanded with the plus 8abcd. And let's have a look at how we can rearrange some of the things here. So notice there's a squared plus b squared all squared here with a minus sign. And here there's a 4a squared b squared. So if we expanded this out, there'd be minus a squared squared, minus b squared squared, and then minus 2a squared b squared. That minus 2a squared b squared would combine with these plus 4a squared b squared to give us plus 2a squared b squared. And then we could write that combination as just minus a squared minus b squared squared. So this term here, together with this 4a squared b squared, can be rewritten as minus a squared minus b squared squared. Similarly, this one here, together with 4c squared d squared, can be written this way here as minus c squared minus d squared all squared. And the other things we'll just keep as they are. Okay, now let's have a look at the top line of what we want this to be. So these are the four terms that appeared as sort of the first half of this big identity expression. Let's call it S, so we have the name. Okay, so let's observe that, say, these two here can be thought of as a difference of squares, because there's a c plus d here and a c plus d here, and there's an a minus b here and a minus a minus b here. So this is really c plus d squared minus a minus b squared. Similarly, this thing here is also a difference of squares. It's a plus b squared minus c minus d squared. This times it's negative. Okay, if we expand this out, there is a minus b squared times a plus b squared with a minus sign. What would happen if we multiplied those two together? Well, the a minus b times a plus b is again a squared minus b squared. The fact that we have a square here and a square here will give us minus a squared minus b squared all squared. That's the result of taking this times this. In a similar way, if we take c plus d squared and multiply by minus c minus d squared, we get minus c squared minus d squared all squared. Okay, and then there's some cross terms. There's c plus d squared times a plus b squared, this times this. And there's plus a minus b squared times c minus d squared. Now let's have a look at these last two terms here. C plus d squared times a plus b squared plus a minus b squared times c minus d squared. Okay, c plus d squared is c squared plus d squared plus 2cd. A plus b squared is a squared plus b squared plus 2ab. Over here we have c squared plus d squared minus 2cd, and here a squared plus b squared minus 2ab. Okay, what happens when we multiply this out? Well, this a squared plus b squared times this c squared plus d squared combined with this a squared plus b squared times this c squared plus d squared to give us 2a squared plus b squared c squared plus d squared. The 2cd times 2ab that we get from here times here, and the minus 2cd times minus 2ab that we get there, combine to give us 8abcd. Plus 4 here and another plus 4 there. The other terms cancel. So the 2ab times c squared plus d squared cancels with the minus 2ab times c squared plus d squared here. And the 2cd times a squared plus b squared here cancels with the minus 2cd times a squared plus b squared here. The conclusion is that this business here is just 2a squared plus b squared times c squared plus d squared plus 8abcd. And what was that? That was all the sort of second half of this expression that we had for s. So putting things together, we had this expression for r involving this and this plus this term here. And then we had this expression for s. This is the same as that. This is the same as that. And we've just now deduced that this part here is in fact exactly the same as this part here. Therefore, r equals s. So yes, indeed, this expression here, which is sort of the first half of the factorization of q of a squared, b squared, c squared, d squared into a difference of squares, that actually factors as a product of these four linear factors. Okay, so that was a lot of fun, a little bit advanced. Make sure you go over that, go through it carefully, write it down. Okay, and make sure you understand what's going on. Your exercise 126.1 is to show that similarly, the second line, when we expanded q of a squared, b squared, c squared, d squared, also factors in a similar way into the product of these four linear factors. These were the other four factors involved in this big Brahmagupta's identity. So this argument, combined with this exercise, proves Brahmagupta's identity. All right, so some onerous algebra, but in a way kind of fun. And so I hope you can go through that, make sure you understand all the steps, and that you are not intimidated by a bunch of variables and having to move things around and taking differences of squares, which is really the only kind of thing that we're really doing here. There is, in fact, a simpler way of establishing an identity like this, which is very important to know about. The simpler proof is to open up a computer algebra package, maybe like Maple, MATLAB, Mathematica, MuPad, Sage, Scientific Workplace, or some other computer algebra system that works with symbolic manipulations, not just arithmetic involving numbers, but polynomial arithmetic involving variables. And then what you do is you basically input this quadruple quad function with arguments a squared, b squared, c squared, d squared, and ask the program to factor it. And it's a lovely thing to see. The program just take 1/1000th of a second or whatever it takes, not very long, and it will factor and give you all 8 of these linear factors for this. Okay, so it's a very powerful tool that becomes increasingly important as we go further in this direction, as we explore further the algebraic mysteries and beautiful interconnectivities that we get from geometry. So now we come to a natural question. Okay, so we've factored this quadruple quad formula with these arguments here. We found essentially 2 factors. The first intimately connected with Brahmagupta's formula. What is the meaning of these other 4 factors? The product of these 4 terms. Well, remarkably, this understanding was only discovered about 20 years ago. In 1995, David P. Robbins, in a lovely paper in the American Math Monthly, established a number of very interesting and novel facts. And we'll talk more about other aspects of Robbins' work in this paper. But one of the things that he noticed is that this expression here is in fact 16 times the square of the area of a non-convex cyclic quadrilateral with side lengths A, B, C, D. If we have a cyclic quadrilateral that looks like this, A, B, C, D, with lengths like that, then it also has an area, and we can square that area and multiply it by 16, and when we do, there's an analog of Brahmagupta's formula for this kind of cyclic quadrilateral, and it involves exactly these four terms here. So the product of these four things is exactly 16 times the square of the area of such a non-convex cyclic quadrilateral. Okay, so we haven't been too precise about what non-convex means here. Well, we can draw a picture like this, but we know we would rather have precise algebraic formulations. That turns out to be not entirely trivial to do and involves notions of betweenness and perhaps notions of interior and so on. So in fact, we're going to keep these this term here, non-convex, in quotes. Okay, in the same way that we had the notion of convex in quotes. Okay. So at least now, though, we have a classical interpretation of the two different factors that we have in the quadruple quad formula. But clearly we have to remind ourselves a little bit about what do we mean by the area of a non-convex quadrilateral like this. Well, we talked about areas of polygons in one of our earlier videos in this series. In fact, in Math Foundations 34, which was called Areas of Polygons. So let me remind you about some of the definitions that we made in that video. So we can start with a triangle A1, A2, A3 in the plane. And let's say its vertices are x1, y1, x2, y2, and x3, y3. And we can think about an oriented triangle. So this is a triangle that's represented with the three vertices, instead of a bar over it, with an arrow over it. And that means that we have a preferred direction for walking around this triangle. In other words, we're going to go from A1 to A2 to A3 to A1 to A2. So we're walking this direction here. Okay. And as opposed to the other orientation would be to walk this way. So basically two oriented triangles that we can associate to the unoriented triangle, just A1, A2, A3. The reason we want an oriented triangle is because the natural notion of area we saw was actually the notion of a signed area. It's really a notion of area coming from linear algebra rather than calculus. Okay. So the definition is that the signed area of this oriented triangle, A1, A2, A3, which we could denote by A, little a, that stands for signed area. And here's the formula for it. It was x1, y2 minus x2, y1 plus x2, y3 minus x3, y2 plus x3, y1 minus x1, y3 all over 2. And if that seems a little bit daunting to remember, it might be easy to remember that if you remember the first two terms, x1, y2 minus x2, y1, then the next two terms are obtained from this one by cyclically permuting the indices, moving the 1 to a 2, the 2 to a 3, and the 3 to a 1. And then going to the next two terms, we just cyclically permute as well. So there's an important special case here when one of the vertices is actually the origin of our coordinate system. So suppose we have a triangle OA1, A2, oriented this way. Okay. Then the area, or signed area of OA1, A2 is, well, it just reduces to x1, y2 minus x2, y1 over 2. These two terms would be 0. And we introduced this notation that we could call that A of A1, A2. It really only depends on this, this line segment, or this oriented line segment from A1 to A2. This kind of expression appears a lot in linear algebra, and for those of you who have seen some determinants, and we will be talking about determinants more later on in this course, but it's probably useful to remark that the numerator here is a determinant of a 2 by 2 matrix. Matrix x1, y1, x2, y2, basically with the coordinates of the 2 points. And then the determinant is this times this minus this times this. And there's a half. If there wasn't a half, then we would be talking about the area of a parallelogram formed by this vector and this vector. Okay, this is very useful to have this sort of simpler notation for the area of this directed line segment. And then we can express areas of triangles and more general polygons in terms of these ones. Okay, so now let's extend that discussion to the idea of the signed area of an oriented quadrilateral. We're thinking about a quadrilateral in the plane, 4 points, with a particular orientation of cycling through those 4 points. So A1 followed by A2, followed by A3, followed by A4, and then going back to A1. That's represented by this notation, A1, A2, A3, A4, with an arrow in that direction. If we went the opposite orientation, well, we would reverse all these arrows, so it would be A1, A4, A3, A2, and back to A1, and so on. Okay, so we can take the definitions of the previous page and apply them to this oriented quadrilateral. We define the signed area of this quadrilateral to be the sum of A of A1, A2, plus A of A2, A3, plus A of A3, A4, plus A of A4, A1. So I remind you that this was actually the area of a signed triangle formed by the origin O, the point A1, and the point A2. So there's a triangle here, which I haven't drawn, but that's what this thing actually represents. And whether that's actually a positive number or a negative number depends on the orientation of things. So we really have these 4 triangles, this one here, and then this one here, and then this one here, and then this one here. And then we're taking the sum of those signed areas and defining that to be the signed area of the total oriented quadrilateral. Okay, so an excellent exercise is to show that this signed area is in fact unchanged if we translate the quadrilateral. That is, if you add the same pairs of numbers to the x and the y coordinates of all 4 points, okay, then these quantities here will change because the triangles all have moved, but the total combination will not have changed. Another way of thinking about that is that it's independent of moving the origin. So if we move the origin around, relocated things, then the signed area of this oriented quadrilateral is not going to change. So it really only depends on the quadrilateral and not its position in the plane. Another way of saying this. Okay, and another specific exercise. Here are 4 points, and just some practice, just calculating what these signed areas look like. So I've given you 6 different sort of ways of going around a quadrilateral. For example, if the points are this one, A1, A2, A3, A4, that would be that sort of non-convex quadrilateral. While A1, A3, A2, A4, that'd be another non-convex one. A1, A2, A4, A3, that would then be what we'd call a convex quadrilateral. Basically sort of 6 various combinations here, so you can practice calculating signed areas. And then the question is, what relations are there between these various 6 numbers? Okay, so now let's think about what happens if we have an unoriented quadrilateral. We have 4 points, A1, A2, A3, A4. But we're not wanting to distinguish between going around this way and going around this way. So if we ask, well, what's the area of such an unoriented quadrilateral, it's a little bit problematic because we've only defined the area in terms of oriented quadrilaterals. It's because we're taking a linear algebraic or geometrical approach to areas here and not a calculus kind of approach. In calculus, you like to take absolute values to ensure that the areas that you get are positive. Unfortunately, taking absolute values takes you outside the realm of pure algebra. So we don't want to leave the realm of pure algebra because we like it. And so we want to get around this difficulty. And here's how we do it. First of all, we note that a given unoriented quadrilateral, say A1, A2, A3, A4, has associated to it two oriented quadrilaterals, namely A1, A2, A3, A4, going around exactly in this direction, or going around in the reverse direction, A4, A3, A2, A1. So if we take the areas of these ones, well, they are going to be negatives of each other. And how we then generate something here is the same way that we generated the quadrants between 2 points from the displacement. You may remember we had 2 points on the line. The displacement between the two of them changed sign if we interchanged the order of the points. By squaring the displacement to get what we call the quadrants, we obtained something that was independent of the reordering. We're going to do exactly the same thing here. So we're going to define the quadria A of the quadrilateral A1, A2, A3, A4 to be, very important definition, 16 times the square of the area of the signed or oriented quadrilateral A1, A2, A3, A4. And that's the same as 16 times the area of the oriented quadrilateral A4, A3, A2, A1. Because these are negatives of each other, and when we square them, we're getting the same answer. The 16 is only here because we've seen that that 16 occurs in Archimedes' formula, essentially Heron's formula, and also in Brahmagupta's formula. There seems to be something special about 16 times the square of the area, so we're going to include it here in this definition of quadria. And you should think of quadria as being roughly quadratic area. But it's not entirely quadratic area because there is this factor of 16 here, which is important. All right, so this is very ultimately natural definition, but it does take some getting used to. That if you have a quadrilateral, the right notion about how big it is in terms of area is not in terms of area, but in terms of quadria. It's actually the square of the area of one of its signed quadrilaterals times 16. Okay, so now we can ask the crucial question, okay, which we've been moving towards. We have Brahmagupta's formula. We have the quadruple quad formula. We have this lovely factorization, which we call Brahmagupta's identity. We saw that somehow there was some similarity between Brahmagupta's formula for the area of a convex cyclic quadrilateral, whatever convex means, and Robin's formula for the area of a non-convex cyclic quadrilateral. Unfortunately, all of those formulas involve the edge lengths A, B, C, and D. And we know in the plane that edge lengths involve square roots. And by now, I hope you're comfortable with the idea that square roots are to be avoided. A square root means that we're moving from pure mathematics to applied mathematics. Square root is something that in general we can only find approximately. Okay? We don't have a theory of real numbers anymore to pretend that we have values for square roots. So logically we are obliged to find replacements for statements involving lengths or distances. And so we have a very explicit challenge in front of us now to come up with a rational version of Brahmagupta's formula for the quadria of a cyclic quadrilateral in terms of the quadrants as Q12, Q23, Q34, and Q41. So I'm giving you this as an exercise. It's quite a hefty exercise, okay, and it's probably something that a professional mathematician can aspire to do, or maybe a graduate student or a very good undergraduate, but it's a bit tricky. You basically have to look very carefully at what I've been doing in this last video and sort of put things together in a very precise way. You have to think very clearly about what really is fundamentally going on. Okay. So in our next video we are going to explore this very interesting relationship that occurs, this sort of formula for this quadria of a cyclic quadrilateral. And I think you'll find it very interesting. It will open up some new doors, and it will turn out to be remarkably connected with some other very interesting developments in the last 20 years in terms of not just areas of polygons, but also volumes of polyhedra, interestingly. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.